Good morning. We solved ordinary differential equations using power series in the previous lecture. Today, we are going to look for the solution of a special differential equation called Legendre differential equation. So the solution to the Legendre differential equation given by 1 minus x squared y double prime minus 2xy prime plus n times n plus 1 times y equals 0 is given by y equals a sub 0 times y sub 1 of x plus a sub 1 times y sub 2 of x. It is a linear combination of two functions since the Legendre differential equation is a second order differential equation. Now, let us look at y sub 1 and y sub 2. So y sub 1 of x is an even power series which is equivalent to 1 minus n times n plus 1 over 2 factorial x squared plus n minus 2 times n plus 1 times n plus 3 over 4 factorial x to the fourth and so on. While y sub 2 is an odd power series given by x minus n minus 1 times n plus 2 over 3 factorial x cubed plus n minus 3 times n minus 1 times n plus 2 times n plus 4 over 5 factorial times x to the fifth and so on. So as an aid for memorization, we note that the numerator of the x squared term is the same as the coefficient of y in the given differential equation. So to determine the other factors, we simply subtract 2 to n and add 2 to n plus 1. We also note that there are no common factors for y sub 1 and y sub 2. Let us have an example. So solve the differential equation given by 1 minus x squared y double prime minus 2xy prime equals 0. Then find the Legendre polynomial. So for our solution, first let us determine if the given differential equation is of the Legendre differential equation form. So let us compare it to the Legendre differential equation. So by inspection, the two are similar with n equals 0. So let us recall the shortcut formula. So this is the shortcut formula for your even and odd expression. So it is a linear combination of two power series. Let us substitute n equals 0 to the derived formula and you will end up with this expression. So y equals a sub 0 times 1 minus 0 x squared and so on plus a sub 1 times x minus 0 minus 1 times 0 plus 2 over 3 factorial times x cubed and so on. So this is the solution if we include a third term that is for x to the fourth and another third term for the odd power that is x to the fifth. So let us simplify. So simplifying the expression, you will end up with a sub 0 times 1 plus a sub 1 times x plus x cubed over 3 plus x to the fifth over 5 and so on. Note that y sub 1 is a finite series while y sub 2 is an infinite series. So the finite series is called the Legendre polynomial, and in this case, your Legendre polynomial is equivalent to y sub 1 of x or p of x sub 0 which is equivalent to 1. The subscript of P implies the degree of your Legendre polynomial, and the degree of the Legendre polynomial is equivalent to n equals 0. Let us have another example. So solve the differential equation given by 10 minus 10x squared times y double prime plus 20y equals 20xy prime. Then find the Legendre polynomial and evaluate it at x equals 5. So for our solution, so let us determine first if the differential equation is of the Legendre differential equation form. So given the expression 10 minus 10x squared y double prime plus 20y equals 20xy prime. Let us use algebra. Let us transpose the expression on the right side to end up with 10 minus 10x squared y double prime minus 20xy prime plus 20y equals 0. So all expressions are divisible by 10. So we will end up with 1 minus x squared y double prime minus 2xy prime plus 2y equals 0. Let us compare it to our formula. 1 minus x squared y double prime minus 2xy prime plus n times n plus 1 times y equals 0. So by inspection, we can say that n times n plus 1 must be equivalent to 2. And if we are going to solve the equation n times n plus 1 equals 2, that will imply that n is equivalent to 1. So therefore, we can recall our formula and we can substitute 1 to n. And we will end up with the expression y equals a sub 0 times 1 minus 1 times 1 plus 1 over 2 factorial x squared and so on, plus a sub 1 times x minus 1 minus 1 times 1 plus 2 over 3 factorial times x cubed and so on. So if we want to extend the expression to x to the fourth and x to the fifth, you will end up with this expression. Now let us simplify. Simplifying, we will end up with an infinite series for y sub 1 and a finite series for y sub 2. So that means our solution is y equals a sub 0 times 1 minus x squared minus x to the fourth over 3 minus x to the sixth over 5 and so on, plus a sub 1 times x. So the finite series is a first degree polynomial because n is equal to 1. And we say that the Legendre polynomial is given by y sub 2, which is equivalent to p sub 1 of x, that is equivalent to x. And finally, let us evaluate the polynomial at x equals 5. That is, p sub 1 of 5 is equal to 5. So based on the two examples, we can have the following generalization. So for a Legendre differential equation, if n is even, then y sub 1 reduces to a polynomial of degree n. While if n is odd, y sub 2 reduces to a polynomial of degree n. And also, we say that these polynomials multiplied by some constants are called Legendre polynomials. So that's all for the discussion of Legendre differential equations. Next time, we are going to discuss another method of solving differential equation, which is called Frobenius method. So this is Legendre Disles. Have a good day.